Thanks for having me here today. Thanks for coming to see my talk. So today I'm going to be talking about computer vision in football. The way I sort of frame this is sort of like I'm sort of trying to give you a bit about my journey learning about computer vision and how to go about using it in essentially in a project generally. And in this case, it's football, something that I love quite a lot. And who am I? I'm again Chris Evi-Parker. My background is actually in scientific software development. So I used to work in weather modeling, then worked in various SD roles in finance. I got really the past couple of years really fascinated in what was happening in deep learning, particularly computer vision, because it was just quite zany what they were doing. And essentially several online courses later, I started essentially a computer vision company, consultancy so to speak, called Cepco Sports Vision. This is actually, again, a lot of this material is past work I did while with this company, Cepco Sports Vision, that I started. Currently I actually work for a private company working in the same field, but this is just on past work I did with an amazing company called Smartodds, which I'll tell you about more. So I started the company just to sort of do independent research. Initially, I wanted to look at action recognition because I also like tennis quite a lot. And so I did that for a bit. And then I said, let me actually find clients who might be interested in investigating this further, i.e., who can actually fund what I'm doing. And who with? It's with an amazing company called Smartodds. They're one of the leading statistical sports modeling companies in the country, and they have a really large video footage archive of football matches, which they used to drive data they derived from these football matches. They used to drive a lot of their betting models. So I approached them with the idea of using CV for data collection, and I created a POC on this. One of the challenges with using video for getting data is video is probably one of the most ultimate unstructured data out there you can work with. And another thing, it's a very memory bound problem because looking through HD level video in time is very difficult. So I created a POC initially just to prove that to Smartodds that this project could actually work, and they gave me a couple videos to work with, and I was able to show that there was some possibility in this idea. So we entered an R&D partnership. So going on to the motivation, the idea of this is quite simple. We have goal side events, usually goal scoring opportunities, and we want to get the player positions from this. So the idea is so player position extraction, simply called. So I want to recover the player positions for specified events. Again, this is goal scoring opportunities, effectively. And here I show the pipeline, which is essentially we have a video stream, we detect landmarks, perform what's called correspondence, we get homography. This allows us to convert points in the image to XY coordinates or pitch coordinates. And what I'm going to actually be talking about is this part in particular, the detection and homography pipeline, and work we did there. So first of all, homography. What is this? It's part of a field called multi-view geometry. And, one way people describe it is that it preserves incidence in P2 to P2 space transformations. And what that means is that parallel lines, essentially, if you think of your eyes, you're looking at a scene. The parallel lines you see in that image that's projected onto your eyeballs remain parallel lines in the other perspective. So if you move across the room, those lines are not going to suddenly change. So that's what homography does. And you've probably seen it being used as virtual billboards on sporting events. So that's how they actually do that. And it's also used in robotics, but in a more complicated field called structure for motion. This is much simpler than that. So again, for how do you do calculate homography? Homography is actually a matrix that's calculated, and essentially what you need is 4 points, which are then related to, in one perspective, is then related to another perspective, i.e. the image pitch coordinates. And essentially, the points have to satisfy a condition, being that they have to be collinear. That is, essentially 3 points in the points you're choosing of the 4 points cannot lie on a single line. As you can see, these points satisfy that rule, and it allows you to do this transformation I'm showing here. And essentially, every point, which is the x here, can be multiplied by the homography, and it essentially transforms those points into onto that spot. Now, that's the easy bit, because there are loads of packages to calculate a homography once you've done the points correspondence. The hard bit is actually determining the landmarks. So if I want to perform this one-to-one correspondence, I need to actually assign identifiers to these landmarks on the pitch, which I'm going to use to do the correspondence. And I came up with a naming scheme or a labeling scheme where I essentially assign these labels to the pitch. Once I did that, and this is just again explaining how the labels here on the pitch diagram relates to an image, perspective on an image, and essentially the problem now descends into detecting those landmarks in the image. So this is pure object detection, and this is where we go into the deep learning bits. So I used so the architecture I'm using, or rather meta-architecture, is a RetinaNet. Architecture is RetinaNet, and I'm using the Keras RetinaNet implementation, which is essentially uses Keras underneath, using the TensorFlow backend. And another package I used was YOLO v3, which was implemented. It was used for a paper called Deep Sort, which was used for tracking in sports. And whenever you approach a project, you always have to decide a meta-architecture of which to use either an RPN meta-architecture or an SSD for the object detector. RPNs, which are called region proposal networks, are the more accurate versions of object detection, but they are decidedly slower than the opposing one, which is called single shot detector. And the frameworks I mentioned before, above, RetinaNet and YOLO v3, are single shot detectors. It can be a bit confusing when you get into object detection on different architectures. This is the underlying architecture of the SSD. This was taken from the original paper, Lu et al. And it shows effectively object detector is essentially made up of, I would say, two things. A backend, which is, if you're familiar with image classification, it's made up of an image classification backend network, which is essentially what they call feature extraction layer. And that's these things like VGG16, ResNet, DenseNet, MobileNet, any of those kinds of backends, as long as they're able to extract features from an image. The next layer is essentially what's called the bounding box regression layer. They come in different flavors. This is probably one of the simplest ones, because this paper is quite old now. But essentially, it uses convolutions to create essentially linear regression against several what they call anchors, which are spread across the image. And that network is now able to regress any of those anchors if any object of interest lies within that anchor's remit, spatial remit. But there's a problem with object detection, particularly for this problem I'm trying to solve, is that the landmarks look locally very similar. And what do I mean by that? If I showed you this image here, these two images, where do you think which label do you think they belong to? A16 or A15? You can sort of tell their goalpost poles. A16, A15 or A15, A16? Yeah, it's not possible. It's actually, you can see it here. That's the goalpost there. Which one? You can't tell. It's so it's actually A15, A16. Yeah. So that's the issue. And what this causes is that effectively to a network, it's noise, because while object detectors do take in a global context, the presence of similar context will make the network not converge fast enough to where you want it to get to. And I'll show you what I mean by that. So how do I solve this? What I do essentially is categorize. So I created a type category. So things that look similar, I gave them the same category, and that's what this mapping you see here is. So, well, next question. Where do I get training data for this? I can't go to there's no benchmark data set for football landmarks, is there? And how much data do I need? Millions, thousands? It's actually not that much. Pre-trained networks, they reduce the need to train from scratch, because getting object detectors to train them from scratch can take days, months. If you're looking at an NVIDIA K80, for instance. So what I used a very handy tool called Mechanical Turk, where I posted work to get done. I essentially, it cost me about 7 cents an image, and given an image, they annotated them quite accurately. And here's an example of a Mechanical Turk agent working. It's actually myself, but this is what it would look like. Actually, when I first started this, I got 2 of my friends to do this. And after 150 images, they told me they'd never touch that again. So very painful work, but I had agents who were able to do about 150 of these in one day. Crazy. But as I said, I'm sort of trying to take you on a journey, and one of the things I wanted to some of the things issues I came into, and I sort of want to bring across was key learnings with crowdsourced labeling. If you ever do this, is you need an efficient review system. Random sample 5% of the workers' jobs to make sure it's good. Again, qualification. This is one great thing Mechanical Turk does. It allows you to have the workers pass a test before they can actually work on any of your tasks. So that really, really helps to weed out bad workers. Some trade-offs. If there's a terminology called master Turkers, you essentially pay Amazon a bit more money, and they'll give you very experienced Turkers. I didn't find that made much difference. And more money equals faster results. It does not mean quality. That's what I found. And here is an example of work I actually gave to do. I gave about 600 images or so. And this is actually slightly unrelated. It was because what part of my work was also to index the football video. And this is one unlucky worker who got found out. And so the excuse he actually gave me, I actually emailed him. He said his wife did it while he was not watching his computer. Yeah, sure. So the answer, its training set is about 1,500. It was about 2,000 images in total, generally for each experiment. So I split it between matches, essentially, and the idea there was to make sure that I reduced the chance of looking at the same stadium test set to avoid introducing model bias, because when I first actually started doing this, I just trained them randomly, and the reality of the performance wasn't where I thought it would be, and this helped quite a lot. Training time is actually, as I said, pre-trained network, about 2 hours on NVIDIA K80. If you're looking at the V100, which is NVIDIA 2080 Ti, it's about half an hour. So about 25 epochs. And obviously there was data augmentation. That helped sometimes, but sometimes it didn't help because data augmentation regularizes your network. And for object detection, it can do that quite badly, that you don't converge, at least not on time. And I had time constraints. So this is the accuracy result on the type categories. And one thing I show here is the direct types are if I try to train on the direct labels and if I try to train on the categories. And as I mentioned earlier, if you try and train on direct types, what happens is that it cannot, the code, it doesn't, it's not able to get a good result because essentially you're feeding it a lot, from the network's perspective, you're feeding it a lot of noise. And you can see it's quite jumpy as it trains, and it has much wider error bars in map values if you're training directly on the labels themselves, rather than the categories I use. And what does the result look like? So this is detecting categories, and that's what it looks like when you visualize it. But I've shown you that bit. I've not actually shown you how to actually then retrieve the labels from all those type categories. So the first attempt I did was something called spatial reasoning, and it's called essentially just relative positioning. So if you're a given category, let's say corner flag at the top left there, what happens is that essentially if all other landmarks are below you and you're a corner flag, then essentially you're A10. Because that's the only thing that makes sense, and you're the A10 label. So that's what I do, and I call this the constraint camera algo, and essentially it's mostly using set theory, and essentially you just solve it directly and it's brute force. You essentially enumerate all possible configuration of category types against a target category that you want to classify for a label, and you're essentially finding unique views from a type category. And what you do is calculate all unique relative positionings, and that creates a set UL, and you then go on the detector, detect the category instances. Then afterwards, for each instance, you detect the relative positioning of other instances for that detection around the instance. That creates another set, and essentially UL is a unique position for a label, so there's no intersection with the other labels. So if set S has a member that belongs in UL, then that instance you're trying to determine is of that label L. Essentially, it means what it means. Sorry if I'm a bit confused, and if you want more on it, you can grab me later. But there's a problem here. I assume a fixed camera pose, which is not true. Like camera positions, I'm saying camera positions don't change, etc. And view angles don't change, and relative positions don't change. None of those are true. But before I go into that, I'll talk about a benchmark metric that I use to actually tell if my performance is good, and it's called MARE, which is mean absolute reprojection error. And what it does is I just essentially calculate the homography ground truth using the ground truth labels I collected from the Turk workers, and then I look at the estimated homography using my pipeline, and I essentially then reproject back into the pitch coordinates and run 10 random points, and I take it's essentially just taking the distance between the reprojected points for estimate and ground truth. And if it's over 10, which is hand wavy, about 10 meters error, I call it a false positive. And this is again just showing what MER looks like in a cartoon form. So points reprojected into image pitch coordinates from image coordinates, and then you get P2 estimates and P1 estimates and P2 estimates, and yeah. So this is what MARE 51.7 looks like. And essentially fails, and because essentially if you look at the labels detected, they're correct, but I didn't detect enough points because of the shadows that came across the pitch. And if you don't have enough points, that doesn't satisfy the collinearity rule, so the homography calculation doesn't converge. And this is an MARE of 1.14, and you can see it's a fairly reasonable approximation of what you would expect in pitch coordinates. So what's the results? These are for two different object detectors. For retina net, for the CV3-fold accuracy is about 76%, and CV3-fold about 71. And YOLO V3 did much better, got 85, and the left out, he actually did better on the left out. I think I didn't have quite enough data when I did this. I had about 50 videos then. But generally, YOLO V3 has far less false positives than RetinaNet is the main reason, and I'll get to that later. So how do I solve this problem with the fixed camera pose? Assuming a fixed camera pose causes a lot of blow-ups, because you're essentially brute forcing a calculation, and if you have false positives, it gets things very wrong. And it was the biggest responsible factor getting bad results. The solution, you can actually model the relative angle distributions, and essentially this is actually used quite a lot in model pose recognition in different fields, and it's quite well known in the probabilistic graphical model community. And what does this look like? Essentially, you're modeling the relative angle of category types to each other, and what it allows you to do then essentially is that this essentially says what's the probability of a landmark being L given that the type categories are detected around it are of this angle. And what effectively happens is that I can't model this. I don't have the data for this, but I have the data for everything else on the right. I can model these distributions. And essentially what happens here is that I model, I use the ground truth data I collected from the mechanical Turk workers and create what are called kernel density estimates. And this is what it looks like. So this is the S2 relative angles to two LFs. And this is actually the histogram here. Then if I use something called KDE SciPy's kernel density estimates package to do this, and it allows me to model it as a probability distribution. So i.e. the density. And using that, I'm able to get better much better results. So this is the cross validation left out. And actually I say better results. If you actually look at it, for the YOLO V3, it's worse, but that's for a very good reason. If you look at the retina image augmentation, this is the previous result, it was 71. I actually get 77 here, and one of the advantages of the probabilistic method is that it does very well against false positives because I'm not brute forcing it anymore. I'm allowing the statistics to bear fruit, and one of the issues is that you need a lot of data. So this was about 2,000 or 1,500 landmarks. That's nowhere near enough because it will still have some hint of bias towards certain camera views. So if I wanted to do this properly, I wanted to actually use like a reprojection, do a camera reprojection of the actual pitch. And sample from that instead. But that was what I got, and I was pretty happy with that because in production we actually used the probabilistic method because it did much better and it's much faster than the brute force method. So some key learnings. I learned measure consistently. One thing I found myself at the start of this project when I started with smart odds was that I used MAP as a general measure of performance. MAP is an accuracy measure for object detection. It's not an accuracy measure for your project or whatever you're doing. And so when you start your project, I think my advice is to start quite early in defining a metric of success for that project. is only halfway through the project I came up with the MARE estimate, which helped me guide me better to solving problems in the project. And one thing, you'll not always understand why it works. It's good to be curious, but at the end of the day, get the project done, because if your pipeline is doing 50%, the client's not going to be happy. And fairly obvious, most of you know this, do out of sample, very important. So the project results, we ran the pipeline against 3 seasons of football. So this is across 43 competitions. So about 18,757 matches effectively watched. It took around 3.5 days to run. About 68% of football events, of 68% of football events were processed. It's currently being evaluated for the downstream better models by Smart Odds, and they have told me they found beneficial signal in the data that's been brought out by the pipeline. So just a video to finish. This was actually something I was interested in, continuous XY, and this is just the result of it, and this is actually a corner kick. Yeah, so that's it, and yeah.
Well, we have time for 2 questions, so if you want to raise your hand, chat in.
So I've got a question on your model architecture. You've covered a couple of convolutional layers.
Yep.
Trying to get as much feature extraction, I assume.
Yeah, that's fine. Yeah.
It's a bit of a 2-part question. So the first question is, did you really require that there's many convolutional layers? Would you perhaps have benefited from some gradient imaging rather than trying to extract features, because gradient imaging would suffice for shadows in particular?
One of the reasons why I actually just stuck, you could do much simpler object detection methods, like maybe half features or things back then with what do you call it, hog features and such. But one thing I love with deep methods, so to speak, is that you get generalization, and it's much easier than trying to handcraft or feature. I don't know if that's what you meant, is handcrafting features.
Yeah.
Good.
What I was really leading into is, would there have been much difference between trying to reduce the image all the way to a 1 by 1 by 128, rather than just stopping at
yeah.
Rather than stopping at accumulation.
So actually, I actually didn't use, so the way I define the anchors is that I define the scale such that I actually ignored pretty much most of everything after here, so it stayed with most of the large scale features. So with Retinate or Keras Retinate, they give you access to all of that, so you can actually just cut out. So what you have is a pyramid feature scale, and you can cut out all the layers towards the back and towards the front, which are higher scale features, and focus on things around like 32 by 32, 64 by 64, anything high, 128, 256, just ignore it. That's why I use the VGG16, which is a fairly cheap network, because to be honest, like solving this is fairly easy. Detecting is fairly easy. Is detecting the different labels. It's the context is the harder bit. So this was actually sort of the easy bit. Yeah.
Well, thank you. Okay, I'll keep it to one question. Do I understand correctly is that, and thank you, it's very interesting, which is why I have so many questions, but do I understand correctly that you're doing it on a single frame by frame basis, and you're not using any probabilistic information in this transfer from frame to frame?
No, so is any like hidden Markov model graphical thing? No. It's generally, I did use something like that and I didn't talk about here, was towards the end, I was going to talk about reading time. So one of the things I needed to do was actually sequence because the events we get have a time index, and I needed to sequence it. There I did use a sort of Markovian style method where essentially I built up confidence over time if I saw a certain sequence of events, which is, yeah, but for this, no, because we have the event time when it happened. We probably could get more accurate by adding time, but it gets very, very expensive once you start to do that. Because the inference time on a K80 for this is about 0.2 seconds for an image. So 1000 by 800. Whereas, if we had a V100, but that's still 50 milliseconds, but over 90 minutes, that's horrible.
Okay. Thanks, Chris.